feeling like sunshine, like springtime, like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong, in my happy place. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong, in my happy place. And I'm right where I belong, in my happy place. And I'm right where I belong, in my happy place.
Welcome to the National University of Singapore Yonglulin School of Medicine's Healthy Longevity webinar. This will be the last one for August, I think, and so thank you for joining us again. We have Professor Jaap van Dieën with us tonight. That'll be an exciting discussion. I'd like to remind you to use the Q&A function to send questions. I'm sure you'll have questions. Before we start with him, though, I want to introduce our speaker at the beginning of the show. Due to technical difficulties that occurred during last week's presentation, we're going to try again. You heard about 30 seconds of Matthias Robert's talk, and then the gremlins took over. He's a research assistant at the NUS Center for Healthy Longevity, and he'll talk about his study, Therapy-Induced Senescent Tumor Cell-Derived Extracellular Vesicles Differentially Suppress Breast Cancer Progression.
Thanks for the introduction. As mentioned, my name is Matt, and today I will be talking about therapy-induced senescent-derived extracellular vesicles. It is widely known that cancer treatment itself could cause cellular senescence, which is termed as therapy-induced senescence, or TIS. When cells become senescent, they secrete a bioactive component called the senescence-associated secretory phenotype, or SAPS, which are pro-inflammatory and could cause fatigue, cardiac morbidity, and physical decline, which could be often observed in cancer patients and survivors, as well as on people with age-related morbidity. While soluble factors in SAPS such as cytokines and chemokines have been extensively studied, not much focus has been placed in the insoluble factors of SAPS, such as small extracellular vesicles, or SEVs. Hence, in this work, we aim to understand the potential effect of SEVs derived from therapy-induced senescent cells. So far, the work in the lab have developed a TIS model of MB231 breast cancer cells by treating with the drug paclitaxel, which is a commonly used chemo agent in the clinic. We found that senescence could be induced by 72-hour paclitaxel treatment, as shown with high beta-gal activity. To isolate SEV, we collect conditioned media, or CM, and subject them into sequential ultracentrifugation, followed by Zeiss exclusion chromatography. We managed to isolate SEV as confirmed by SEV markers in the fraction 7 to 12 and confirmed by nanoparticle tracking analysis. These isolated SEVs could be observed through scanning electron microscope, which could be seen as rounded and cup-shaped vesicles. We then use zebrafish and mice breast cancer models to evaluate the function of these isolated SEVs. In the fish model, we incubate stained MB231 cells with conditioned media, TIS SEV, and CM where SEV fraction has been depleted before injection into the yolk. We found that cells preconditioned with TIS SEV exhibit lower invasion and migration index in the fish as compared to TIS CM and SEV depleted CM. This then suggests that TIS SEV are able to mediate different paracrine effects compared to the soluble fraction of the SAPs. We also used 41 breast cancer mouse model where mice were subjected into 6 intratumoral injection of SEVs. And consistent with prior data, we could observe that these SEV injections are able to reduce tumor growth in mice as measured by weight and volume. When we stain the mouse tumor tissue, we surprisingly found that there is an acquisition of senescence markers in the TIS SEV group, such as increase in beta-gal staining, reduction of proliferation marker Ki67, and increase in DNA damage marker gamma-H2AX. We also observe an increase in P65 staining, which is a sign for increased inflammatory signaling. And this P65 activation is also accompanied with a significant increase of infiltrating CD8 positive T cell lymphocytes, suggesting immune cell activation. To conclude, we found that therapy-induced senescence-associated SEVs are able to exert anti-tumor effect in zebrafish and mouse breast cancer models. And current efforts are also ongoing to identify the effect of these SEVs on inflammation in the non-disease normal physiological context. For further reading on this study, you can check out our paper as shown on the slide. I'd like to thank all of the people who have been involved in this project. Thank you very much.
Thanks. I realize now I've had 2 shots at saying that title and I missed it both times. So we may have to have his presentation on about 6 more times before I can say the title of the talk correctly. Jaap van Dieën is a professor of biomechanics at VU in Amsterdam. His main research interest is the control of balance in walking and standing, with a special focus on the control of trunk, posture, and movement. Dr. van Dieën has successfully supervised over 60 PhD students and has published over 550 papers in scientific journals. Tonight, he's going to talk about feedback control of walking and how it's affected by aging and how we can maintain it. Thanks for joining the show, Jaap.
Thanks for the introduction. I will now share my screen. So yes, indeed, I'd like to talk about feedback control of walking, and I will speculate a bit about how training can affect the effects of aging. So we all know that walking and our ability to walk is a vital sign. Specifically, gait speed predicts mortality. But of course, our ability to walk is also a determinant of our participation in society and consequently of our quality of life. Now, at old age, say over 75, there are clear problems in gait. Usually people at older age walk slowly, they spend more energy to cover the same distance, so they have a high energetic cost, which leads to a low endurance. They cannot walk as far. But maybe most importantly, the incidence of falls during walking is very high. But how does gait change over the lifespan? Unfortunately, there's not a whole lot of data. So these are 2 results from my own group, where we looked at different age cohorts and we looked at daily life gait. So what we see here is the total duration of walking during a day and the number of walking bouts during the day as a function of age on the x-axis. Now you can see from these graphs that roughly in the 5th decade, there's a decrease in gait performance. So people start to walk less and less often. If we look at how well they can walk, so this is more in a supervised condition reflecting their ability to walk, the 20-meter walk test, data from another study showing gait speed here on the left and stride time variability on the right. And stride time variability, important to note, is a predictor of falls. So what we see here overall is a decline in the ability to walk from the 7th decade on, so quite a bit later. And then there's a third result I wanted to share with you, which is on challenged gait. So this is the previous graphs were, let's say, on either unsupervised gait in daily life or supervised gait as fast as possible. But what if we challenge gait? And in this study, this was done by split belt walking. So split belt walking is walking on a treadmill with one belt running, for example, at normal gait speed, and the other belt running at a slower speed. This leads to an asymmetry in step length that gradually resolves over time. So people slowly adapt to this perturbation. In addition to this step length asymmetry, what we can also observe is that the medial lateral margin of stability changes. And basically that means that they start to step wide relative to, let's say, the center of their body or their center of mass with the foot on the slow side. And this effect increases with age. And this is roughly a linear increase, so we might presume that there's a linear decline. Interestingly, when looking at normal gait, normal walking in the same study, there was no effect of age detected. So what does this walking with wider steps actually mean? Why do we walk with wider steps when our gait is challenged? Well, the reason for that is that if we separate where our center of pressure is, that's the position of the where the ground reaction force applies to our feet relative to our center of mass, we use that as a mechanism to stabilize gait. Let me explain this a bit further. So in this diagram, we see the center of mass. During walking, this center of mass moves towards the lateral edge of the base of support, and that could do a fall in the sideward direction. So we have to break this movement towards our stance foot. We can do that by shifting the center of pressure underneath the stance foot, as illustrated here. So I'll go back. So we can shift the center of pressure a bit, which then generates a horizontal force pushing our center of mass back towards the middle. But we can also do that by shifting the position of our foot, so by stepping wide. And actually this is the dominant mechanism to control stability during walking. So walking with wide steps is robust. And you might ask why we do not always walk with wide steps. Well, the simple answer is it's energetically inefficient. It costs a lot of energy. So what we tend to do during normal walking is actually coordinate where we place our feet relative to what the movements of our center of mass are. So in this graph, we see time on the x-axis. We see the trajectory of the center of mass in the medial-lateral direction as this sort of periodic function here, and we can see some variation in the movements of the center of mass. So what we've tried to do is to predict where this foot will be placed, which you see illustrated with these lines. So blue line is the position of the right foot, red is the left foot. And we try to predict those positions from what the center of mass is doing during mid-swing. And those positions are indicated with the stars. Turns out that the position and the velocity of the center of mass combined predict quite well where we place our foot. So the variation in center of mass movement during walking is sensed by our central nervous system and is then used to adjust foot placement to control our balance during walking. And this is captured in a very simple linear equation, a linear regression model, you could say, which says foot placement, which of course occurs when we place our foot at heel strike, is a linear function of the position of the center of mass during mid-swing and the velocity of the center of mass during the mid-swing. And of course, this has some error attached to it. This model describes normal gait quite well. It gives us some more information. It gives us the gain of the position and velocity feedback, and I will get back to those. But most importantly, maybe for now, is the goodness of fit of this model tells us how well the foot placements are coordinated relative to our center of mass movement, and those can be quantified as the relative variance accounted for or the residual error, the root mean square of the error term in this model. This is a typical example in the graph of a young subject. All the red dots are left foot placements, all the blue dots are right foot placements. On the x-axis is actual foot placement, on the y-axis is the predicted foot placement by this model. And in the first study we did on this, we found an average R squared in 12 healthy young adults of 0.73. Now, if we compare that with older adults, and here we see two typical examples, the same young participant, and here we have an older participant over 65 years of age. And what we can see is that the residual error of the model is larger in the older participants. And this was true at the group level. So older adults coordinate their foot placement less accurately relative to their center of mass movement while walking. Now, the error was also not zero in young adults. So apparently there's other mechanisms at play. And in the beginning, I already mentioned that we can also shift the center of pressure underneath the foot, and we can do that by changing moments around the ankle joint. So our hypothesis was that we would correct for errors in foot placement by changing the ankle moments during the subsequent stance phase. So we again looked at gait of healthy young participants, in this case 30 young adults walking at normal and slow speed on a treadmill. We applied the same model to predict foot placement from the center of mass position and velocity. That gave us an error in foot placement, and we used that error in foot placement to predict the shift of the center of pressure due to ankle moments during the subsequent stance phase. This is one typical example showing that indeed there is a relation between this error here on the x-axis and the shift in the center of pressure during the subsequent stance phase. So this additional mechanism is used to correct for errors in foot placement. And this gave us an idea. So if these ankle moments correct for foot placement errors, what happens if we constrain those ankle moments? So if we make it impossible to change those ankle moments. And to do so, we use this very simple intervention. We had a shoe with a narrow ridge underneath the sole of the shoe. And the ridge was about 1 centimeter wide, so the center of pressure cannot be shifted more than, let's say, half a centimeter in either direction. But the foot can roll off normally because this ridge is made of rubber and hence is flexible. And these are two typical examples of normal walking, the center of pressure trajectory during two normal steps, one where it moves quite far to the medial direction and one where it stays on the lateral edge of the foot, and this is the fore-aft direction. This is walking with this narrow ridge, or our, as we call it, the less shoe with the narrow ridge. You can see that the center of pressure in the medial lateral direction is constrained. So now there's no correction for errors in foot placement. And our hypothesis was that this might help people to learn to place their feet more accurately. So we did a pilot study in older adults. 10 older adults visited our lab for 4 weeks, consecutive weeks. During the first week, we only looked at normal walking on a treadmill, also as a baseline. And then in weeks 2, 3, and 4, we had a short training intervention. They walked for during 2 sessions for 5 minutes with these shoes with a narrow ridge, with some rest in between, and 2 sessions during that week. The next week, the ridge was made a bit more narrow, and we repeated the same protocol. And then the fourth week again, the ridge was a bit more narrow still, and then we repeated this. And this shows some of the results. So this is the standard error, a standard deviation of the residual error. So a measure of how well foot placement is coordinated to center of mass movement. And as we can see, this standard deviation of the error, so the residual error, decreased over time with training. And also at 2 weeks after the intervention, this effect was still significant relative to the baseline. So it was retained. We also looked at an independent measure of gait stability, which is the local divergence exponent. And here, higher values mean less stable, low values mean more stable. And what we see during the training period is that normal walking on the normal shoes became more stable. Unfortunately, this effect, well, we could not show retention as it was not significantly different from the baseline at 2 weeks post-intervention. Anyway, this pilot experiment showed promising results with a very short and low-cost intervention. We found that foot placement and gait stability improved during training, that retention may be incomplete in this short intervention period. And I have to remind you, we had no control group, and we also did not look at falls during follow-up. So this is still very preliminary. But an interesting question is, could this generalize to feedback control in response to large perturbations? Because here we were looking at corrections by foot placement during unperturbed gait. So just dealing with the effects of neuromuscular noise, which causes variance in the center of mass trajectory. Now, this is actually the line of research that we started with many years ago, and this is one video from those experiments. So here we see a young adult walking over ground, and you could see an obstacle popping up to trip this person, and who actually subsequently regained balance and continued walking. This is from a similar experiment in an older adult. And as you can see, this gentleman is able to regain balance, but only just. And of course, quite a number of our older participants actually fell during these experiments. What we learned from these experiments was that balance recovery after large perturbations can be classified as a quite complex skill. It involves qualitative changes in muscle activation, in kinetics, so in joint movements, and also in kinematics, in the movements performed. It involves muscle activity from the lower legs to the upper arms, and it involves large muscle forces and rapid force development. We also found that there are meaningful differences between individuals within an age group, but also between age groups in the capacity to regain balance after these large perturbations, which could not be predicted accurately from, for example, muscle strength. These results really indicate that task-specific assessment and training is probably needed. So probably the feedback models that we apply for unperturbed gait cannot be simple, and the training that we applied there cannot be generalized to these large perturbations, which may eventually lead to falls. So we also did a training study looking at larger perturbations. So this is a perturbation-based training protocol that we called REACT. We can see two video clips of participants here. We see the mechanical perturbations, we see them walking on the treadmill, and they're performing a dual task at the same time. This is a cognitive task that they played with a handheld controller. This was a 4 weeks perturbation training, and we assessed the effects on balance and gait performance, self-efficacy, physical activity, and gait quality, and falls in daily life. So this is the whole protocol. During the first week, we did clinical assessments of balance, so balance test and gait performance tests. We had the subjects received an accelerometer that they wore for 1 week to record gait during daily life. And then they were trained in a local physiotherapy practice for 4 weeks. One group participated in the REACT training, so that's treadmill walking with perturbations and a dual task. The control group had the same treadmill walking and the same dual task, but no mechanical perturbations. In the next week, we repeated the clinical assessment of balance and gait. We repeated the accelerometry measurements, and subsequently we performed a follow-up of falls during 6 months. So here are the results. In red, we see the control group. In blue, we see the REACT group. But it's easiest to look at the crosses and the stars. The crosses indicate a main effect of training without interaction. So both groups improved. The mini-best, the reactive part of the mini-best. But there was an interaction for the SPPB, with the REACT group improving more. If we looked at gait confidence, both groups improved. If we look at falls efficacy, there's more effect in the in their training in the REACT group, so in our experimental group. And GSE, finally, again, an improvement in both groups. If we look at the daily life measurements, I can be very brief about this. Basically, we found no effects in either of the groups on daily life gait performance. But we did find an effect on falls, and we did find a significant interaction with the REACT group improving more in terms of the average number of falls, which decreased from 2 to 0 post-intervention in the training group and stayed constant in the control group. And also the number of fallers improved significantly more in the REACT group. So the training of reactive balance control to large perturbation, we first of all found that, well, this is task-specific. We found it to be safe and effective. It improved balance and gait performance. It reduced concerns about falls, but it did not change daily life gait. However, it did reduce the number of falls and fallers. So where does this bring us? Well, first of all, feedback control of gait can be improved in older adults by imposing constraints or perturbation, or in other words, by challenging their gait during training. I think an important question is, can the deterioration be prevented instead of remediated in old age, and what would be needed for that? And this brings me back to the start of my presentation. So what we found in looking at these studies is that it seems, and this is all a bit speculative, it's comparing between different studies and different cohorts, but it seems that activity, so how much do we walk during daily life, or also how fast do we walk, because movement intensity is a measure of speed during daily life walking here, decreases already quite early on, the 5th decade, whereas speed in supervised walking, so more our ability to walk at a certain speed, decreases much later. So how much we actually do versus what we can do seems to differ. And this may suggest that maintaining or increasing the volume and speed of outdoor walking might actually help to prevent the decline in our ability to walk at these speeds. And I could not resist putting in this slide. This is from a preprint that I came across only last week, which reports a natural experiment on the effect of the built environment on physical activity, and in particular on gait. So what these authors did is they monitored changes in physical activity from mobile phone data in people moving from one city to another in the US. So here we see an example of people moving from different cities to New York City. And the opposite here, people moving from New York City to other cities across the US. Now, all the cities in the study have been ranked or graded according to walkability. And New York City happens to be a very walkable city. There's broad sidewalks, there's space to walk, etc. So what do you see in people that move from less walkable cities to New York City? They actually start to walk more. And people that move away from New York City to other cities, they walk less after their relocation. This is the result from the whole study. So we see the change in walkability. So with the relocation, there's a change in walkability of the city that these people live in versus the change in steps. And we can see a nice correlation between these two. So, and again, I'm speculating here, but I'm suggesting that we really have to consider city design as maybe one of the most effective ways to increase the quantity of walking. But I'm also speculating that this may help to increase the quality of gait in people, or maintain the quality of gait. With that, I would like to thank you for your attention. These are the names of the people that contributed to the experiments that I reported, and these are the funding sources.
Thanks. Yeah, that city experiment's fascinating. It's a really clever idea to think about that. I'll come back to that later. One thing to start with, I try to catch acronyms as they go along because a lot of our guests don't think in this area that much. So a couple I heard during the perturbation study was SPPV, which I know what that is, and GSE. Can you just define those briefly for people that don't know what they are?
Yeah, so SPPB is the short physical performance battery. It's a series of tests of physical performance, including tests like I think the timed up and go, if I'm correct. So getting up from a chair, walking, turning around, walking back to the chair and sitting down again are part of that. Postural sway is part of it. So it's measures of balance and gait performance, basically. And the GSD is to be honest, I forgot what that abbreviation means.
We'll figure that one out.
I'd have to check. Anyone can.
Sanjay, you got 10 minutes to solve that one.
People can send me an email. I can complete that.
I was thinking about this, and you always hear that people as they get older have more falls. And do we know when they're falling? Are they falling walking when they trip over something, or getting up out of a chair, or going up the stairs?
We have some data on that. There's some studies that used questionnaire data in people after endurance falls. Those are on community dwelling elderly, and there it's the vast majority is during walking. And those are often trips and slips. That's about, I think in total, about 85% of all of those falls in community dwelling elderly. There's also some data from people living in residential care facilities in Canada based on surveillance camera data there. Again, walking is an important, let's say, task during which falls occurs, but also transitions from, for example, sitting to walking are a major cause in that group.
I was thinking about I'm here in Bangkok now in a hotel, and I was just walking outside, and I can barely survive walking out here. There's not one flat sidewalk in the whole city, and if you manage to survive the sidewalk, you have to deal with the motorbikes. So but you see people out here walking a lot, even older people, so they navigate it. I think they get plenty of practice.
That's maybe sort of the message I try to give in the end, or in the end, it's sort of, you have to be exposed to these risks and to maintain the capacity to deal with them. So it's finding the balance between, let's say, exposure that you could consider a risk, or completely losing the capacity and then falling over your own feet, basically.
And I guess you mentioned a lot of things that happen, that cause people to reduce their walking as they get older. Could be painful. They're reducing energy. I mean, it takes longer to get someplace. How much of it is motivation and how much of it is physical or pain?
Well, the fact that we already see this during the fifth decade, to me, suggests that a lot of this is cultural and motivation related, and not so much related to morbidity or pain. That's probably true at older age, because then, of course, the prevalence of those problems also starts to increase. But in the fifth decade, I would suggest that cannot be the main cause. So I think
the opposite. I want to walk everywhere in cities when I travel now. I probably walk more than I did when I was younger. I thought the split belt walking experiment was really interesting. I was trying to decide how hard that actually is. It looks pretty hard, actually. How long does it take someone to adapt to it?
Well, in fact, it's not really hard, but what you see in the beginning is a very large asymmetry in step length, and that disappears gradually. I'd say it takes about half an hour to sort of reach an asymptotic value in young adults. And of course, this then is related to an asymmetry in the step times on both sides, because you have to accommodate that. It's been used a lot as let's say, as a motor adaptation paradigm in walking. Personally, I'm not very fond of it because it's a very artificial task. It's not related to anything we do in daily life, where perturbations are typically transient and often unexpected. So I think something like targeted stepping, where you have to step on, for example, virtual stepping stones and avoid virtual obstacles, which is also a gait adaptation task, is a more ecologically valid model to test these kind of things. But there are as far as I know, no data on those kinds of adaptations over the adult age span.
It seems like a very minimal set of experiments you could do to train people. I mean, the I guess what the Leshuk testing, the walking in certain places and not others. All of these things are relatively low cost interventions. Are they employed that much? I mean, is what's the impediment to getting this tested in people?
So the
I mean,
treadmill
are
that
not tested, but scaled to a larger population.
So the treadmill that I showed does perturbations by accelerating and decelerating the belt. That requires, let's say, a bit more advanced than
Yeah.
normal treadmill. It can also project obstacles and stepping stones on the treadmill, so you can also use it for gait adaptation. Um, so this is on the market. It's used here in the Netherlands, for example. We see it in rehab centers where it's used to train patients. In what we did in this study was we placed it in like a local physiotherapy practice, and we invited older adults in the neighborhood who were, let's say, had levels of physical activity or some fall history to participate in the training. This is not common. This is not commonly done, and most physiotherapy practices will not have this type of equipment. Over here also, it will not be reimbursed by insurance companies who have unfortunately limited interest in prevention anyway.
Yeah.
Um,
You
but
beat me to that one.
in my mind, this is completely feasible to do once we sort of put the right, probably reimbursement structure in place.
Yeah, and if you go to physiotherapy centers, my father had to go to them a couple times when I was back visiting him in Indiana. And there's no reason you couldn't put something like that in there. I guess you have to have more precautions so people don't fall and injure themselves. But
Well, it has a safety harness, so they
yeah,
don't fall, of course, and the physio needs to be trained in using the protocols, but
yeah.
it's very doable. Yeah.
I was a little surprised in comparing the intensity walking, I guess one of them declines earlier than the other, right? And then you also have the split belt walking, which is a linear decline. They're all doing different things, and I guess it made me curious what's going on with the split belt walking declining early. But I guess that probably has a larger component of perception, and you know, it
Yeah.
requires other aspects of your body that probably are less relevant, at least from a conscious point of view, in the other assays. I wonder if the earlier decline is related to that.
Well, the idea is that this is really sort of challenges the proprioception. So you sort of have to sense, let's say, that asymmetry in step movement and adjust it appropriately. You do not. I mean, in some studies, people have blocked visual feedback on where the feet are, and you still adapt to it. So you can do it based on proprioception. That may be different from, of course, that's, let's say, a modality that is specifically challenged in this paradigm. Also, I think it is cognitively quite demanding. It's disrupted quite strongly by performing a simultaneous dual task, for example. So that may be the difference. If you look at all three, the first is what people do in daily life. So it's basically what they choose to do. Then the second one was the 20-meter walk test, in which they're told to walk as fast as possible. And then, of course, but it's still, let's say, normal walking without any external challenge other than this instruction. And then the third one was the split belt walking, where there's really an external challenge. And for the same outcome parameter in the same cohort, normal walking did not show similar trends. So I think it's really related to the challenge of the conditions.
Yeah, that split belt walking would be a good drinking game. So, sorry. Okay. couldn't resist.
Narrow beam is the more traditional one, I think. But
So the foot placement, this is also probably affected by fatigue. So when you have someone who's fatigued, they're probably more erratic in foot placement, I would guess. Does that correlate with someone who's older but not fatigued, or are there different changes that happen?
so what we found in the study on older adults, I did not present those results, but what we did, we vibrated their hip abductor muscles during the stance phase, so on the contralateral side. Our expectation was that you would actually use proprioception provided by those muscles or muscle spindles in those muscles to sense, let's say, your medial lateral movement. So what we find is if we vibrate those muscles, people make a systematic shift of their foot placement on the opposite side inward, and older people do so less. So it seemed that in them, at least one contributor to this is that either their proprioception is less good, or they use it less well. We've also, in other studies, shown that fatigue of these muscles has an effect on the proprioception from those muscles. So I would expect that localized muscle fatigue of these muscles would definitely affect the foot placement accuracy as well, but we have not tested that yet.
You mentioned that in the, I think you said Leshuk training, if I'm pronouncing that correctly. Um, you mentioned that some of the effects that you saw didn't persist over time, but over the 2 weeks after the training, it was a kind of a short training, and it made me think that some sort of intermittent reinforcement, would probably maintain those, you know, probably at a relatively small level of intermittent reinforcement, you could keep those effects over the long term.
Yeah, no, I would agree. And I'm also not sure whether we're not looking at a type 2 error here. I mean, this was a very small pilot study, of course. We did see a trend with the local divergence exponent still being lower at the 6-week time point than at baseline, but it was not significant. So we cannot say that the effect was retained. But in general, I think some sort of booster sessions after training of probably any type are needed, and definitely for more skills-related training. There's some indications from perturbation training, like the second type of training that I showed some data from, that indeed these booster sessions can help to maintain effects over prolonged time.
I was looking at the city changes, and one thing that struck me is that the walking went down when people moved from San Francisco to somewhere else in California. Yeah, San Francisco it's a walkable city in some ways, but it's pretty darn hilly too. Is there any correlation between the hills you're walking and the quality of the walking? Did they look at that at all?
I'm not sure to what extent slopes are accounted for in this walkability index. I did not look at the specific of that. They actually used public repository data in the study for this walkability index. San Francisco was ranked as quite a walkable city relative to many others, which from personal experience, I would also agree with, I guess. Yeah, but I don't know how the hills do affect those scores.
For one thing, in San Francisco, the weather is always tolerable to walking. It's never too hot, never too cold. And
They did
you see a lot of people walking there, that's for sure.
there was some analysis of potential effects of climate on the outcomes, and that did not have a strong effect. So it seems that the effect of walkability was, let's say, robust against differences in climate between cities.
It's an interesting study. I think people walk a lot in New York because it's faster than trying to drive anywhere. So it's
That could be another intervention. Just have more traffic jams, and then.
So let's bring in Sanjay to ask some questions from the audience.
Hi, Professor. So thanks for your presentation. So yeah, one of the question from audience name is Steve. So he mentioned that as we get older, there are more joint pain during walking, knees and hip. What do you recommend to reduce the joint pain and joint pain during walking? So is it like
Well, to begin, I'm not a clinician, so I can only say what I know from the literature, which is limited because that's not really my area. But what I do know, for example, knee osteoarthritis, is actually that physical activity training, but also walking programs, do have positive effects. I do also know that this is true for low back pain, that walking programs do have positive effects. So it seems in general, actually, that maintaining a decent physical activity level, although it may lead to some initial pain provocation, is actually beneficial. And this may have to do with the effects of exercise on inflammation, for example.
Yeah, I think another thing that people say, and I don't know if this is true because I'm not an expert either, is that maintaining muscle integrity and strength in around joints keeps the joints from, especially the hip from and knee, from doing things they shouldn't be doing, which could be creating benefits as well.
and another question what do you mention the lay shoe training? Am I correct?
Yep.
And can be although it's a pilot experiment, what do you think if it is going in a right direction? So can we use this training for the in movement disorder diseases as well in future?
The first thing we would like to do is an RCT in healthy older adults. This is what we're trying to get funding for currently. I'm not so sure about. I would be a bit hesitant with any sort of patient group for now, because obviously there is some risk involved. Now, the pilot experiment we did here in the lab under supervision on the treadmill, and I think it was quite safe. But obviously, the promise of a simple tool like this, because these are very cheap to make, could be that people could just do it in their home environment or in outdoors in the daily environment. And there I would be very hesitant to move into, let's say, doing this in groups that are more at risk of falling than healthy older adults. But yeah, obviously, it could also be done in a supervised way, and then this might be a tool. There's some evidence using another challenge of foot placement, but actually a mechanical one where an external device pulled the foot away from let's say, the optimal foot placement according to the model. This is data from Jesse Dean's lab in Charleston. They did this in stroke patients, and they also saw improvements in foot placement with these mechanical perturbations. So there's some promise also in pathological conditions there for a very similar intervention, you could say.
A little bit something off question companies shoes companies, but brand like Nike and Puma, they also claim if you wear their company shoes, they increase your performance. So are they also follow that same kind of foot error placement concept? It's just curious.
No. As far as I know, no company has been looking at this. We've been actually discussing this with a shoe manufacturer, but this has not led to any results. I don't think I guess the problem is that there's not a clearly marketable product here, because on the shoe itself, you will perform less.
Yeah.
Right? But it trains you to perform better when you walk on normal shoes again, which is useful for training purposes. And it could be that some manufacturer would be interested in producing these shoes for training, but definitely not for performance.
Okay, thanks. Another question from attendee, he want to know how the balance recovery affect in a person with benign paroxysmal position and vertigo. It's kind of disease that related to the ear, and if you change there's a disbalance between the. So what do you suggest?
So we've done one study on a population of people with dizziness complaints, which were chronic and not some are, let's say, idiopathic in nature. So these people were treated in a rehab center where the focus was basically on learning to live with the problem, so more psychological counseling and management. And in that center, they integrated a walking training program with the idea to make them less visually dependent. And this was, I think, sort of, purely clinical experience or clinical opinion. And what they did is they had visual perturbations during walking on a treadmill with a virtual reality environment. What they do see is clinical improvement in this population. Now, again, uncontrolled, even not really in a study context, but in the clinical context. And they asked us to look at the idea that this visual dependency would change over time. And what we do see indeed is that their center of mass movements, as the treatment progresses, become less entrained with the visual perturbations that they apply. So it seems that the feedback models that I talk about assume that we can estimate somehow what our center of mass is doing. And proprioception will contribute to that, and we've shown that with this model, as I alluded to earlier. The vestibular organ will contribute to that. The visual information will contribute, and probably perceptions from the sole of the foot of the stance leg will also contribute. And that information is integrated to get an estimate. And overly relying on single modalities like vision, which also happens with aging, actually, people also become more visually dependent, may be, let's say, perturbing when you're in a visually very busy environment, for example, where everything is or everything and everyone is moving. Then you don't have reliable visual input to estimate your, let's say, the vertical. So training people to use, let's say, other sensory, or let's say a mixture of different sensory inputs, or relearning to do that may be beneficial, but this is quite speculative still.
Another question, like, will the unpower or power exoskeleton also improve the gait in older people who might otherwise be unable to walk unassisted?
So that's one of the things we've been working on in a collaboration with biomedical engineers who are working on exoskeletons. Exoskeletons now are, let's say, quite good at generating propulsion, but a user has to use crutches to stabilize themselves. So and the problem is there's no balance control. So you have to use crutches, which means you cannot carry anything, you cannot open a door easily. And that actually leads to most people that have trained with these exoskeletons actually prefer their wheelchair for most of what they're doing in daily life. So one of the ideas is if you could implement these control algorithms that we derive from human gait in the exoskeleton, so you could use, let's say, a biomimetic approach to have the exoskeleton control balance in a way that is intuitive to the human user, that this might make these exoskeletons much more usable. Now, I don't foresee a future where we will do something like that in healthy older adults, but like if you think about spinal cord injury or partial spinal cord injury, there's obvious applications there, and maybe even in stroke recovery.
So another question, like, is there like suppose like people like do athlete and like the bodybuilder, they take supplements as well, and in older age, like if you like provide the supplement, like that will strengthen your muscle, and with the combination with your this food placement error, so can be helpful for like this movement age diseases and walking means like movement associated diseases or kind of like that.
Well, first, muscle strength is crucial for balance control, and especially for balance recovery after large perturbations. So like I mentioned, in these experiments on tripping, we see very high muscle activity especially of the calf muscles, the hamstring muscles, that are activated at a very high rate, and they produce large joint moments that change rapidly. So muscle force, muscle strength, and muscle power are limiting factors in balance recovery, especially. So it does make sense to do muscle training or anything you can do to maintain muscle condition. But there are also, let's say, motor skills, and strength alone is not sufficient. You also need to maintain that skill. So I think a combination is needed, and that's also what the literature shows in general. If you look at systematic reviews on exercise interventions to prevent falls, the indication really is that you need what they call balance training, so that's a skills training, and that muscle strength training has an additional benefit to that.
Okay.
Yeah, I think the other challenge in the older population is how much they respond to strength training and or supplements or amino acid diets. A lot of older people have trouble absorbing amino acids anyway, and so a lot of the diets that bodybuilders take may not be so effective. And it's another discussion whether the bodybuilders should be taking some of these things, but we'll leave that for another show.
Okay. Thank you so much for your answer. So I'm hand over to Brian again. So Brian, go ahead.
Yeah, so I'll have one last question. I'm watching this perturbation. How much do people adapt to that? I mean, they have to. Their responses. Can you look at the time of adaptation and see if that changes in the context of aging or?
Well, what we try to ensure is that it remains to be purely adaptive. So we make it unpredictable. We change direction of the perturbation randomly. And in the training, we increase the intensity of the perturbations, and we also increase gait speed. So we make it more and more challenging over time. I think that's needed. And what we see is that we can clearly progress in terms of training difficulty. We could also make the dual task more difficult over time, and their performance improved on the dual task as well. That's also interesting to see. We see no evidence of any anticipatory control in terms of adopting a different gait pattern that would allow them better to, like walking with wider steps, for example, that would allow them to deal with these perturbations more easily. And that's, I think, because we apply them only, let's say, occasionally and not too often.
I guess that's part of the reason for the dual test, right? It keeps them from anticipating so much what's happening. So.
That was one reason. The other was also we thought that this would help transfer to real life, because often you're not just walking, you're, let's say, scanning traffic at the same time.
Have them look at their phones.
Yep. Which is an extra challenge because you lose visual information and you take away cognitive resources as well. Yeah.
Yeah, well, yep, it's great to have you on the show. It was a really interesting discussion on a topic that we don't hit very much. So I think the audience have learned a lot, hopefully. And we'll have you come back sometime. Thanks a lot for joining us.
Thanks for the opportunity.
I want to remind people to use the chat function and choose the panelists and all attendees option to leave comments and feedback so that everyone can view it. Next week, we have a return guest, Professor John Wong, who's the Isabel Chan Professor in Medical Sciences. He'll be talking about aging Singapore, challenges and opportunities. And I'm going to leave you with a final video about every move counts, but in this case, only if it makes a sound. Thanks a lot.
like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong, in my happy place. I got my head held high, I'm on my